Nearly 15 billion miles from Earth, in a region so far away that sunlight itself takes more than 20 hours to reach it, a spacecraft built in the 1970s has picked up something that scientists did not expect to find. NASA has now confirmed what Voyager 1's instruments detected just beyond the edge of our solar system, and the finding is forcing researchers to rethink what they thought they understood about where our cosmic neighborhood ends and the rest of the galaxy begins. In this video, we're going to walk through exactly what Voyager 1 picked up out there, why it caught NASA's scientists off guard, and what it actually means for our understanding of the boundary between the Sun's territory and interstellar space. If you enjoy real verified space discoveries rather than science fiction, stick around till the end. What makes this story worth telling carefully is that headlines about Voyager tend to swing between two extremes. On one side, you get dry, technical press releases that undersell just how strange these findings actually are. On the other, you get sensationalized clickbait that throws around words like impossible and anomaly without explaining any of the actual physics behind them. The truth sits somewhere in between. These are genuinely surprising, scientifically significant discoveries, but they're also fully explainable once you understand the environment Voyager 1 is actually flying through. To understand why this detection matters, we first need to understand where Voyager 1 actually is. Launched on September 5, 1977, Voyager 1 originally had a fairly modest job: fly past Jupiter and Saturn, take some pictures, gather some data, and complete its mission within a handful of years. Nobody involved in that original plan expected the spacecraft to still be operating nearly 5 decades later, let alone that it would end up making history as the first human-made object to leave the bubble our sun creates around itself. That bubble is called the heliosphere, and it's essentially a vast region of space dominated by the solar wind, a constant stream of charged particles that the sun blows outward in every direction. As you travel further from the sun, that outward pressure of solar wind gradually weakens, until it can no longer push back against the pressure of the interstellar medium, which is the thin soup of gas, dust, and cosmic rays that fills the space between stars. The boundary where those two pressures balance out is called the Heliopause, and on August 25, 2012, Voyager 1 became the first spacecraft to cross it, officially leaving the heliosphere behind and entering interstellar space. You might assume that once a spacecraft crosses such a boundary, that would be the last major milestone worth talking about. Mission accomplished, headline written, story over. But that's not even close to what actually happened. In the years since that crossing, Voyager 1's remaining instruments have kept collecting data from a region of space that no spacecraft had ever sampled directly before, and what they've picked up has repeatedly surprised the very scientists who built and operate this mission. The first surprise came almost immediately, and it had to do with magnetic fields. Before Voyager 1 crossed the Heliopause, researchers largely expected that the magnetic field of interstellar space would look completely different from the magnetic field inside the heliosphere. Different strength, different orientation, a clean break marking one region from the other. Instead, Voyager 1's magnetometer picked up something odd. Scientists eventually worked out what was going on, and the explanation turned out to be more interesting than the original prediction. Researchers, including Merav Ofer at Boston University, proposed that the Sun's magnetic field and the interstellar magnetic field are connected through structures now nicknamed magnetic highways, essentially tube-like channels formed where the two fields reconnect and merge at the boundary. Instead of a hard wall separating inside from outside, the heliopause behaves more like a porous membrane, letting particles travel along these connected field lines in both directions. This was not something anyone had confidently predicted before Voyager actually got there and measured it directly. The physical process behind this is called magnetic reconnection, And it's actually a well-known phenomenon in plasma physics. It's the same basic mechanism responsible for solar flares on the sun's surface. When two magnetic fields with different orientations come into contact under enough pressure, their field lines can break and reconnect in a new configuration, releasing energy in the process and effectively linking regions that would otherwise be magnetically separate. The second major surprise, and the one that's generated the most headlines in recent reporting, involves temperature. When Voyager 1's plasma instruments sampled the region right around the heliopause, they detected particles moving at speeds consistent with temperatures somewhere between roughly 30,000 and 50,000 Kelvin. Because that number sounds so extreme, a lot of outlets have taken to calling this region a wall of fire, and in a loose sense, the nickname fits. That is, an extraordinarily high temperature by any everyday standard. But here's where the actual science gets more nuanced than the dramatic headlines suggest, and it's worth slowing down to get this right. Temperature in physics describes how fast individual particles are moving, not how much heat they can transfer to something else. In this region beyond the heliopause, particles genuinely are moving at very high speeds, so the temperature reading is technically accurate. However, the density of those particles is incredibly low. We're talking about a handful of particles in a space that would be crammed with trillions of times more matter if it were sitting in Earth's atmosphere. Because there are so few particles to actually strike the spacecraft, there isn't enough energy transfer happening to burn anything. Voyager 1 passed straight through this superheated zone completely unharmed, its instruments and structure no worse for wear. This distinction matters a lot because it tells us something fundamental about how different space is from our everyday intuitions about heat and fire. A region can register extreme temperatures on an instrument and still be, for all practical purposes, harmless to a solid object passing through it, simply because there isn't enough material there to transfer that thermal energy in any meaningful way. It's one of those cases where science fiction language wall of fire ends up technically true and yet still deeply misleading if you don't know the physics behind it. Think of it this way. The inside of a very hot oven and a lit match both involve high temperatures, but you'd much rather stick your hand briefly near the oven's hot air than touch the match's flame directly, because the flame is dense and concentrated, while the oven air, despite being hot, has far fewer molecules actually making contact with your skin at any given moment relative to a direct flame. Multiply that difference by an almost unimaginable factor, and you get something close to what Voyager 1 experienced at the heliopause, a region where the average particle really is moving incredibly fast, but where those particles are spread so thin that they can't deliver enough combined energy to harm anything solid passing through. The third detection, and arguably the one with the most lasting scientific impact, concerns the density of interstellar space itself. For decades, the working assumption among astrophysicists was that interstellar space would be almost perfectly empty. A near-total vacuum with only the faintest trace of scattered particles. Voyager 1's plasma wave instrument, however, detected something scientists weren't expecting, a persistent faint hum of oscillations coming from the interstellar plasma surrounding the spacecraft. This wasn't a one-time blip. Researchers led by Stella Koch-Acker at Cornell University documented this continuous signal and used it to directly measure the density of the plasma out there. What makes this hum so scientifically valuable is that it gives researchers a way to measure plasma density without needing a dedicated density instrument, which is important given that Voyager 1's original plasma science instrument stopped reliably functioning back in 2007. By analyzing the frequency of these oscillations, scientists can calculate how many charged particles are present in a given volume of space, essentially turning a background hum into a precise measuring tool. Acker described the signal as behaving something like a gentle, persistent rain, sometimes louder, sometimes fainter, but essentially always present in the background. What they found was that interstellar space, at least in the region Voyager 1 has been traveling through, is measurably denser than the models had predicted. It's still an incredibly sparse environment by any Earth standard, but it's not the empty void that older theoretical models assumed. This single finding actually forced researchers to revise long-standing models of how the heliosphere interacts with the surrounding galaxy, because a denser interstellar medium pushes back harder against the outward pressure of the solar wind, which in turn affects the shape and size of the heliosphere itself. Taken together, these three detections, the unexpectedly aligned magnetic fields, the superheated but harmless plasma region, and the surprisingly dense interstellar medium, paint a picture of the edge of our solar system that is far more dynamic and far more complicated than scientists assumed before Voyager 1 actually got out there. The heliopause isn't a simple, static shell separating us from everything else. It's an active, breathing boundary that responds to changes in solar activity, that has its own internal structure, arc, and that connects to the wider galaxy through mechanisms nobody had directly observed before this mission. It's worth pointing out that Voyager 2 has added valuable context to all of this, too. When Voyager 2 crossed its own heliopause boundary in November 2018, 6 years after Voyager 1, it took a completely different route out of the solar system. Because Voyager 2's plasma instrument was still fully functional at the time, unlike Voyager 1's equivalent instrument, which had stopped working reliably back in 2007. Voyager 2 was actually able to directly measure plasma density right at the moment of crossing, giving scientists a second independent data point from a different location around the heliosphere. Comparing data from these two crossings has helped researchers build a more three-dimensional picture of what this boundary actually looks like, rather than relying on a single slice of measurements from one direction. The differences between the two crossings turned out to be scientifically valuable in their own right. Voyager 2's data showed a somewhat different density profile and a less dramatic magnetic field transition compared to what Voyager 1 experienced, reinforcing the idea that the heliopause isn't a uniform shell, but a surface whose properties genuinely vary depending on where you cross it. Having two independent spacecraft launched at the same time but taking different paths turned out to be an enormous advantage that nobody fully appreciated back when both missions were originally designed purely to study Jupiter and Saturn. One thing that makes all of this especially remarkable is just how limited Voyager 1's remaining capabilities are at this point in its mission. This is a spacecraft that was designed and built using late 1970s technology, running on a plutonium-powered generator that loses roughly 4 watts of usable power every single year. NASA has had to progressively shut down instrument after instrument just to keep the spacecraft's essential systems alive long enough to keep transmitting anything at all. And yet, even with this dwindling collection of aging instruments, Voyager 1 has managed to hand scientists to genuinely novel data about a region of space that remains completely inaccessible to any other spacecraft humanity has ever built. This raises an obvious question. Why does any of this actually matter beyond simple curiosity? The answer has real practical implications. Understanding the structure and behavior of the heliosphere isn't just an academic exercise. It directly affects how much cosmic radiation reaches the inner solar system, including Earth. The heliosphere acts as a kind of shield, deflecting a significant portion of high-energy cosmic rays that would otherwise bombard the planets, including any future crewed missions traveling through deep space. If the heliosphere's shape, density, and magnetic structure are more complex and more variable than previously modeled, then predictions about radiation exposure for future astronauts, say on a long-duration mission to Mars or beyond, need to be revised using this new, more accurate picture. This isn't a distant hypothetical concern either. Space agencies planning multi-year crewed missions beyond low Earth orbit need accurate radiation models to design spacecraft shielding, plan mission durations, and set safety thresholds for astronaut exposure. Cosmic rays, unlike the radiation most people are familiar with, can be extremely difficult to shield against completely, since they consist of extremely high-energy particles capable of penetrating substantial amounts of material. A more accurate understanding of how the heliosphere's boundary filters and modifies incoming cosmic radiation gives engineers better data to work with when designing the next generation of deep space habitats and spacecraft. There is also a broader scientific payoff here that goes well beyond our own solar system. Every star in the galaxy that produces a stellar wind likely creates its own version of a heliosphere, a protective bubble carved out of the surrounding interstellar medium. By studying our own heliosphere's boundary in this level of detail, scientists gain a working model for how these bubbles behave in general, which has implications for understanding the environments around other stars, including ones that might host planets of their own. NASA's confirmation of these findings has also directly shaped how the agency is thinking about the next generation of deep space missions. There have been ongoing discussions and proposals for a dedicated interstellar probe mission, one specifically designed from the outset to study this boundary region with modern instruments, more sensitive detectors, better power systems, and a design built around what we now know, rather than what scientists assumed decades ago when the Voyager missions were designed. In other words, everything Voyager 1 accidentally discovered while just trying to survive out there is now actively informing how humanity plans its next deliberate expedition to the same neighborhood. Such a proposed mission would likely carry instruments specifically built to measure the exact phenomena Voyager 1 stumbled upon somewhat incidentally. Dedicated plasma density sensors that don't rely on indirect calculations from background hum, more precise magnetometers capable of mapping the magnetic highway structures in far greater detail, and possibly even instruments designed to directly sample interstellar dust and its composition. If such a probe were launched using a faster propulsion system than Voyager's original trajectory allowed, it could potentially reach and cross the Heliopause in a fraction of the time it took Voyager 1, arriving with instrumentation an entire generation more advanced than what's still limping along on these aging 1970s spacecraft. It's also worth addressing something that inevitably comes up whenever headlines use phrases like NASA confirmed, alongside something described as unexpected or anomalous. None of this points to anything genuinely inexplicable or paranormal. Every one of these detections has a grounded physical explanation rooted in known plasma physics and electromagnetism, even if the specific numbers and behaviors weren't what earlier models predicted. Science regularly produces results that don't match expectations, and that's not a sign that something is broken or mysterious in an unsettling sense. It's exactly how scientific progress is supposed to work. A surprising result means a model needs refining, not that the rules of physics have been suspended. That said, it's easy to understand why so much coverage leans into dramatic language. A 50-year-old spacecraft drifting through a region of space no human has ever visited, detecting a scorching wall of fire. It somehow passes through unscathed. Sounds like something out of a science fiction film. The genuinely wild part is that this isn't fiction. This is documented, peer-reviewed, real data being sent back across nearly a full day's travel time at the speed of light by hardware running on technology older than most people watching this video. Let's talk a bit more about how this data actually reaches us, because the process itself is part of the story. Voyager 1's instruments record their measurements, and the spacecraft's aging computer system packages that data for transmission. It's sent using a radio transmitter running on an almost impossibly small power budget by modern standards, and it's picked up by NASA's Deep Space Network, a system of 3 massive radio antenna complexes strategically placed in California, Spain, and Australia, so that at least one of them can always be pointed at Voyager 1 as Earth rotates. Given the spacecraft's current distance, each individual signal takes roughly 23 hours to arrive. That means every discovery we're discussing happened, from Voyager 1's perspective, nearly a full day before scientists on Earth even received the data confirming it. By the time it reaches Earth, Voyager 1's signal is astonishingly faint, on the order of a fraction of a billionth of a watt, far weaker than the signal from a modern cell phone, by many orders of magnitude. Picking up something this weak requires the Deep Space Network's most sensitive receiving equipment, careful noise filtering, and precise pointing accuracy, since even a tiny misalignment could mean missing the signal entirely. The fact that any usable science data makes it back to Earth at all across a distance this vast, using hardware from an era before the Internet existed, is itself a remarkable feat of 1970s engineering combined with decades of careful, ongoing maintenance on the ground. This delay adds an interesting dimension to how these discoveries get announced and confirmed. Scientists don't get real-time updates from Voyager 1 the way you might imagine monitoring a live video feed. Instead, they receive periodic bursts of data, which then need to be processed, calibrated, and cross-checked against other measurements before anyone is confident enough to publish results or make a public announcement. The wall of fire detection, for instance, wasn't announced the moment it happened. It emerged from months of careful analysis of the data Voyager 1 had already sent back, with the researchers working to rule out instrument errors and confirm the readings were genuine before going public. It's also worth noting that Voyager 1 almost didn't get the chance to make these detections at all, at least not in the form we know today. Back in 2007, the instrument specifically designed to directly measure plasma density stopped functioning reliably. Since then, scientists have had to get creative using the plasma wave subsystem, which detects oscillations rather than directly measuring density, combined with mathematical models to infer plasma density indirectly. It's a testament to the ingenuity of the mission's science team that they've managed to keep extracting meaningful publishable results from a spacecraft with a permanently broken primary instrument for the exact type of measurement they needed most. Looking ahead, NASA has been candid that Voyager 1's remaining operational lifespan is limited. The spacecraft's power output continues to decline every year as its plutonium fuel source decays, and mission engineers have had to methodically shut down instrument after instrument just to keep the spacecraft's most essential systems, its transmitter, its attitude control, its remaining sensors, functioning as long as possible. Estimates suggest Voyager 1 may only be able to keep at least one science instrument running into the early to mid-2030s, and possibly less, depending on how gracefully its aging hardware continues to hold up. Every instrument shutdown decision NASA makes at this stage is really a decision about which remaining scientific questions matter most. With extremely limited power left to work with, engineers have had to prioritize the instruments most likely to keep producing genuinely novel data about this interstellar environment, while retiring instruments whose scientific returns have started to diminish. It's a careful balancing act between preserving the spacecraft's ability to communicate at all and preserving its ability to still do meaningful science, and so far, the team managing this decades-old mission has managed to strike that balance remarkably well. This means that whatever Voyager 1 detects in these coming years may represent some of the last direct measurements humanity gets from this region of space for a very long time. Any future interstellar probe mission, even if approved and funded soon, would take years just to reach the same distance Voyager 1 already occupies, and additional years beyond that to actually cross the heliopause itself. There is a real possibility that we will lose direct contact with this specific region of interstellar space for a meaningful stretch of time before a successor mission can pick up where Voyager 1 leaves off. That's part of what makes this confirmed detection so significant right now. It's not simply an interesting scientific curiosity. It's some of the last first-hand data we're likely to get from this exact vantage point for the foreseeable future. Every reading Voyager 1 sends back between now and whenever its power finally runs out adds to an irreplaceable dataset that no other spacecraft, current or currently planned, will be able to replicate anytime soon. There's also something worth appreciating about the sheer improbability of this whole situation. A spacecraft built using slide rules and technology from an era before personal computers existed is still successfully detecting subtle plasma oscillations, magnetic field alignments, and temperature anomalies in a region of space that lies beyond the practical reach of virtually every other instrument humanity has ever built. The engineers who designed Voyager 1 in the 1970s couldn't have possibly predicted the specific discoveries their spacecraft would make decades later, and yet they built something robust enough and flexible enough in its instrumentation to still be scientifically useful in an environment they could only theorize about at the time. It's a reminder of just how much value there can be in over-engineering a piece of hardware meant to explore the unknown. Voyager 1's designers had no way of knowing exactly what conditions the spacecraft would encounter at the edge of the solar system, since nothing had ever traveled there before. Rather than building instruments narrowly tuned only to what they expected to find, they built a suite of general-purpose sensors capable of measuring magnetic fields, particle densities, and plasma waves under a wide range of possible conditions. That flexibility is exactly why, decades later, this aging spacecraft was still able to pick up phenomena nobody anticipated when the mission was first designed. Let's answer a few common questions people tend to have about all of this. Is Voyager 1 actually in danger from any of these conditions? No. As we covered, the wall of fire region is thermally intense, but far too sparse to physically harm the spacecraft, and the magnetic field changes detected so far haven't posed any operational threat to Voyager 1's systems. Does this mean the edge of the solar system looks the same in every direction? Not necessarily, because Voyager 1 and Voyager 2 cross the heliopause at different locations and different times, and their data shows some differences. Scientists now believe the heliosphere's boundary is asymmetrical rather than a perfectly uniform sphere, possibly shaped more like a comet or a croissant due to the Sun's own motion through the galaxy. Could future missions detect something even stranger out there? It's entirely possible. Voyager 1 and Voyager 2 are working with instrumentation designed in the 1970s, and both are down to just a couple of functioning science instruments each at this point. A purpose-built interstellar probe with modern sensors could measure this same region with far greater precision and might reveal details these aging spacecraft simply can't detect with their remaining capabilities. Is any of this related to claims about mysterious energy fields or unexplained phenomena you might see in more sensationalized reporting? No. Every finding discussed here has a well-established basis in plasma physics, electromagnetism, and thermodynamics. The surprises here are about degree and structure, not about anything defying known physical laws. So to bring this back to the original question, what exactly did NASA confirm Voyager 1 detected beyond the edge of our solar ice system? The short answer is a region far more complex than anyone expected. A boundary where magnetic fields connect rather than sharply divide, where temperatures soar into the tens of thousands of degrees without posing any real danger due to the extreme sparseness of matter and where interstellar space itself turns out to be measurably denser than decades of theoretical models had assumed. None of it is supernatural or unexplainable. All of it is real, confirmed, peer-reviewed science, gathered by a machine that was never even supposed to survive long enough to make these observations in the first place. If you found this breakdown interesting, make sure to like the video, subscribe to the channel, and let us know in the comments, of these three discoveries, the magnetic highways, the wall of fire, or the denser-than-expected interstellar plasma, which one do you find the most surprising? See you in the next video with another real space story worth exploring.